All right, so well, we're continuing on, and now we're getting into exponential equations. All right, now there are two types of exponential equations that when we graph them, this is two ways they can look. So I've got a graph here. We have, like I said, two different types of exponential type graphs. The first one is what we call a growth graph, exponential growth. And that is when your graph starts off low and then it grows, but exponentially, which means it goes up very, very rapidly. The more it goes up, or the farther along it goes, the faster it goes up. And then there's what we call exponential decay. Oops, decay. Didn't spell that one right. And it works the opposite way. It's basically flipping this graph over where it goes down very rapidly at the beginning, and then it just decreases a small amount as we go on. So there's our two different types of graphs. Now, the equation that could possibly create either one of these graphs is in the form y equals a times b, and of course we need an exponent for exponential equations, to the power of x. All right. Now, these values, because we are going to develop an exponential equation, is that the a value is what's called your starting amount. All right, so there's your starting amount, is your a value. Your b value is called your multiplying rate. Now, x will determine how many times you're going to multiply that rate, but b is your multiplying rate. Now, if b, first of all, b has to be greater than 0. We'll put that in there first. B has to be a positive number for an exponential equation. Now, if b happens to be greater than 1, you have a exponential growth equation. And if b is less than 1, but of course greater than 0, that's when we have an exponential decay equation. All right, so there is the form of our exponential equations, and all you need to figure out, well, not all you need to figure out, but is your starting amount and your multiplying rate. All right, so there's the form of the equation. So we're going to look at developing some exponential equations and actually working with them. So I'm going to get to my example number 1, which again is going to be a real life situation. All right, so we're dealing with a house. Again, it helps if you have the note with you so you can read along with me. All right, so we get to, like I said, example number 1. And example number 1 says, a house bought at the end of 2010 for $200,000 has increased in value at a rate of 4% per year. How much should the homeowner expect their house to be worth at the end of 2021? So somebody bought a house for $200,000 at 2010, at the end of 2010, 2021, want to know how much this house should be worth. All right, now, again, when we're coming up with an exponential equation, excuse me, it's going to be in the form y equals a times b to the power of x. Now, again, the a is your starting amount. And this house starts at a initial rate of $200,000. That's what it's worth initially. That's your starting amount. That's not a problem. Now, b is. We have to come up with a multiplying rate. All right, now, this house, each year, you are going to still have the house, so you have 100% of that house. But this question is saying that your house is increasing at a rate of 4% a year. So not only are you going to have 100% of your house after year 1, or after any year, you're going to have an extra 4%, which of course means after every year, you're going to have 104% of that house. You're going to have the house plus 4% more. Now, this is something that I've taught many times, is that percent is useless as to use in math equations. You have to convert it to a decimal. And to convert 100% or any percent to a decimal, we divide by 100. And so if I take 104% and divide it by 100%, I get 1.04. That is our multiplying rate. So now our equation looks like this. Y equals 200,000 times my multiplying factor, which is 1.04 to the power of x. That is developing and creating our exponential equation. Now the question further says, how much is the house going to be at the end of 2021? Now, we know the price of the house after 2010. And what we want to know is because it's increasing at 4% a year, how many years have gone by? Well, between the end of 2010 and the end of 2021, 11 years go by. So our x value that we're looking for is 11. That's a specific. The equation is for this house in general, where we can figure out the value after 2011, 2012, what we think 50 years from now, if the multiplying rate stays the same. But here specifically, we're looking for 11 years after 2010. And so in my equation, I am now going to substitute in an 11 for x. All right, and then to solve this equation, again, following Bedmus, I have to do my exponent first. So I have my $200,000 here, and then I take 1.04 and to the power of 11, and I get, let's see here, 1.04 to the power of 11. I think on my sheet I messed it up. I did to the power of 10. It is 1.54. Rounded to 2 decimal places. And then I multiply that 1.54 by 200,000. And I get $308,000. That is what we would expect the house to be worth at the end of next year, if, of course, the multiplying rate stays the same. All right, so we develop our equation. Then we're looking at a specific scenario, plug it in, and we solve. All right, now I'm going to try another one of those. Example 2. All right, so example 2, all about an ant colony. All right, so it says an ant colony begins with 120 ants. And hopefully you've never had an ant colony in your house. It's nasty. But increases at a rate of 18% per month. How many ants will there be 1 year later? All right, so again, I need to develop my exponential equation, which again is going to be in the form y equals a times b to the power of x. Now, again, my a is my starting amount. B is my multiplying factor. Now, this says that they're started off with 120 ants. Now, my multiplying factor is saying that this ant colony is increasing at 18% per month. And so my B value, unfortunately, I'm going to have 100% of those ants plus 18% more per month. And so in total, I'm going to have after each month, I'm going to have 118% compared to the month before. And again, I can't, that needs to be converted to a decimal because it will not work in an equation. Percentage useless to us that way. And dividing by 100%, I get 1.18. And so now I can write my exponential equation. Y equals, again, my starting amount. I had 120 ants, unfortunately, times B, which is 1.18 to the power of x. And again, see how my v value is above 1? It's an exponential growth function, unfortunately. All right, now we've developed the exponential equation. The next step is to solve the question here, where it says how many ants will be there in 1 year. Now, I'm not going to put a 1 in for x, and here's why. This is 1 year. this rate, this particular rate is based on per month. So my X value has to be in months. So 1 year is 12 months. All right, so now I'm going to substitute that into my equation. I have 120 times 1.18 to the power of 12. All right, and so again, solving here, I'm going to do my exponent first, the 1.18 to the power of 12. And I get, let's see here, 1.18 to the power of 12. I'm getting 7.29. And then, of course, finally, multiplying 120 by that 7.29, I'm looking at roughly 874 point, you can have decimals here, no, it doesn't make sense, 0.8 ants. All right, so again, that one, we have an exponential growth going on because it's increasing. But again, we got to watch it for our X value that we're substituting in, because if the rate is per month, then we need to have our X value in months. All right, let's try another one of those. All right, so example number 3. Example number 3. All right, so example number 3 says, and unfortunately this is roughly true, a brand new car, worst investment you can make, loses 15% of its value each year. How much would a car purchased for $30,000 be worth after 6 years? Usually a car loan is around 5-6 years. All right, so this is something you want to know, what's the value of your car, so you can sell it before it's worth nothing. All right, now again, the equation, y equals a times b to the power of x. A is our starting amount. This brand new car, it starts off being worth $30,000. Now b, the multiplying factor. Here's where things get a little different. It says that the brand new car loses 15% a year. So you start off with your car being worth 100%, full value, right? But each year, you're losing 15%. So I'm minusing 15%. All right, now 100% minus 15% is 85%. Again, I have to convert that to a decimal. Dividing by 100, I get 0.85. All right, so now I can write my exponential equation that I have here. I have y equals my a value, again, 30 grand, times b, which is now 0.85 to the power of x. Again, notice when you look at the b value, it's less than 1, which is telling us this is an exponential decay because the value of your car is decaying. As it gets older, it's not worth as much. All right, now, to solve a specific situation, it wants to know how much would this car be worth after 6 years. Our multiplying rate is per year, and so our x value is simply 6 because they're both in years. All right, so now I'm going to substitute in a 6 for x. And so I have y equals 30,000 0.85 to the power of 6, because we're looking at 6 years. All right, so once again, I'm going to do my exponent there first. And so 0.85 to the power of 6, I'm looking at 0.38 to 2 decimal places. And now the value, I take 30,000, I multiply it by 0.38, and now this $30,000 car is worth, or projected to be worth, $11,314.49. All right, so again, that's an example of an exponential decay, because again, the b value less than 1. All right, now, Example 4. We get into a little something different. We get the same. Nice and dry. All right, so example 4. Now, these are mostly true values here. In example 4, we're talking about the Earth's population. All right, now, it says in 1981, the population of Earth was 3.5 billion people. After 29 years, the population of Earth doubled to 7 billion very quickly. And by the way, I don't think the world hit 1 billion till about 1880, somewhere in there, and then hit 2 billion around 1935. So we're getting big quick. But anyways, so the population of Earth was 3.5 billion in 1981. After 29 years, the population of Earth doubled to 7 billion. How many people are expected to populate the Earth in the year 2020? Now, there's a specific equation for this type of problem, and here it is. We have what's called n is equal to n naught, all right, times 2 t divided by d. Oops, t divided by d. Now, n is considered your final amount. N with a little 0 here, which is actually n naught, which here's a little useless information for you. In the last few years, or not last few years, few decades, we had the 70s, the 80s, the 90s, and then we had last decade, not this one. I don't even know what they call this one, but they were called the noughts. So 2005 was in the noughts. N naught. And 0, again, this is going to be, because again, it's like your A value, it's your starting amount. And, well, because we're talking about when the Earth's population doubled, that's why there's a 2 there. T is the time that's gone by, time elapsed. And D is what's called your doubling time, how long it took for something to double. All right, so there's a new equation for you. It's called your doubling time formula. All right, now, in this question, we'll get back to it. We want to know the final amount in 2020. So I'm going to go over here. We don't know this year what the final amount will be. And not though. We do know that in 1981, that's when our first perspective is, 3.5 billion people were around. All right, so 3.5 billion. The time that's gone by. Well, from 1981 to 2020, what are we looking at? So from 2000 to 2020, that's 20 years has gone by. Down to 81, that's another 19 years. So 39 years have gone by. And that again is from 2020 from 1981. That's the difference. Now, D is our doubling time. How long did it take to double? Well, the question says here that it took 29 years to go from 3.5 billion to 7 billion people on Earth. And so that took 29 years to double. So that is what's called our doubling time. The amount of time it takes to double. All right. Got everything here. Now, it is time to substitute in to see how many people we should have in 2020. So we got n equals n naught. I'm going to put, our final number is going to be in billions. So I'm going to put a 3.5. All right. Once again, our doubling time is 2. Right. So that's our multiplying factor because you're multiplying by 2. And then we have t divided by d. So I'm going to have a 39 divided by 29. All right, so now I'm just doing bedmas, but I'm going to have to simplify that exponent first. And so I've got n is equal to 3.5 times 2, and then my exponent there is going to be 1 point, let's see here, 34. Now again, simplifying, so I have 2 to the power of 1.34. Definitely going to need your calculator for that. And it ends up being 2.53. And then finally, I multiply those two numbers, and again, this is the population in billions, and I get 8.86 billion people are projected to be on the Earth right now. The only problem with this question is that our doubling time of the Earth, our population is actually shrinking. It's getting, we're populating the Earth much faster than we used to. All right, so that is what we call an example of a doubling times formula. Now we're going to go the other way here in example number 5. All right, so we'll look at example number 5. Now let's see here. Instead of doubling, we're going to go the other way. Let's see here. All right, so here we go. So example number 5. So we're talking about radiation here. There is 200 grams of radioactive material called radon, which has a half-life. So now we're not doubling, we're cutting in half. It has a half-life of 3 days. How much radon would be left after 19 and a half days? All right, so now we got another formula coming at you here. We have N is equal to N naught. Those are going to be the same. It's going to be the final amount and the starting amount. Now, because we're talking about half-lives, half, 0.5, make sure I get that in there nicely, no? Is going to be our multiplying factor because we're cutting it in half each time. You're losing 50%. And our exponent here, instead of being T over D, we're going to have what's called T. I'm just going a little crazy out here. T over H. And so now, the T is still the time elapsed, but now we're looking at what's called the half-life of the material, or the half-life of the population. All right, so there's a new formula for us. So very similar to the doubling times, except for D is replaced by H, and instead of a 2 as our multiplying factor, we are now having a half, because this is now exponential decay, because things are getting smaller. All right, now back to the question. There is 200 grams of radioactive material. That is our starting amount. So, again, we're looking at the final amount. All right, so again, we're looking for the, that's dead. Let's see, switch it up here. There we go. So again, we're looking for the final amount. N naught, that is our starting amount. We're starting off with 200 grams. The time elapsed. How much time's gone by? Well, it said 19 and a half days have gone by. Our half-life is that this material has a half-life of 3 days. So it cuts in half every 3 days. Your T and your H, because we're dividing them in the formula, must be in the same units, all right? So if we have days and hours, either have to both be in days or both be in hours, because we're dividing. All right, now I'm going to substitute in to my equation here. So I have N is equal to N naught. We started off with 200 grams of this stuff. Our multiplying factor is 0.5. And then to figure out how many times it is being cut in half, we have T divided by H here, which is now 19.5 divided by 3. And just as I did before, I'm going to figure out the exponent first. So I have 200 times 0.5 to the power of 19.5 divided by 3. I would get 6 point something. Actually, 6.5. All right, and so now I'm doing the exponent, so I have 200 times 0.5 to the power of 6.5, and I'm going to get 0.011. And then finally, I multiply 200 by that 0.011, and I get 2.21 grams of that material. And there we go. So there is an example of our half-life. So we got exponential equations, and then we just went into specific ones of a half-life and a doubling time formula. But again, you can come up with simple exponential equations by finding A, your starting amount, and B, your multiplying factor, which either, again, can be growth or decay, depending on whether in the situation it is the starting amount is increasing or if the starting amount is decreasing. All right.